Hello, everybody, to our next brand new chapter. We are going to move on to a new topic that hopefully gets us thinking about problem solving in a way that you might not think is helpful, but is actually the most helpful. And it also leads us into our discussion on probability. So we are going to talk about sets and events. These two things are really the same. Started. So when we talk about a set, that is not pretty writing, is it? Wow. This needs to warm up. Talk about a set. It is simply a collection of objects. Now, those objects could be abstract. We can talk about letters of the alphabet and collection of letters. We can talk about animals, talk about a collection of animals. It could be people, it could be tables in your house, or if you have multiple tables, it could be anything. These objects are called elements of the set. So, with our initial discussion, I have to introduce some key words for this topic. Some words that we are going to use often in our language, so to speak. Even though it's still English, we have certain words to refer to certain key concepts in this topic. First word is set, and the next word is elements of the set. So usually we use a capital letter to name a set. Let's look at some examples. Let's look at the letters of the alphabet and let's define some sets. I'm going to use a big A as the name for my first set, and the elements, which will be lowercase letters of the alphabet. Let's say it's little a, little b, little c. I'm going to, whoops, that's ugly. I'm going to put them in curly brackets to clearly identify what the objects are, this set, what is the collection. Now, when we list them, there is no arrangement. For me to keep track of the letters, I put them in alphabetical order, but it could be CAB, BCA, just the collection of letters. It doesn't matter the order in which you write them, they're floating around. You write them in any way you want. No ordering here. So big B, we'll call maybe this set of letters little a, little b, enclosed in its square brackets, curly brackets. Let's say big C. Let's go with C, D, and E. My curly brackets are not very good. They deteriorate very quickly. And let's say big D is the set, just a collection of little letters. Let's say X, Y, and Z. So within this example's context, I am looking at lowercase letters of the alphabet. There are more, many different collections I can make. These are some of them. So now we have two extreme concepts. Now I'm going to keep this example so that we can just jump back and forth as we need to look at it. So I'll make a new page for the rest. We have two extreme examples. First is the universal set. universal set. That's simply the set of all possible elements in question, in relation to the topic. If we're talking about lowercase letters of the alphabet, then if we continue our example, the universal set will be all the lowercase letters of the alphabet. Now there are 26 of them and I'm too lazy, so I'll use my little dots to indicate the clear pattern and show where it ends. But it's not a sequence. A sequence implies there's an ordering of these. There's no ordering, but I'll list them in a logical way, of course. They could be shuffled. Anyway, it's still the same collection. The letter that we'll reserve for this, let's make a little bit more space here, so that we don't have to redefine it. We'll call it U for universal set. When you talk about this topic in a more statistics setting, then they use an S for sample space, but I doubt that's going to be necessary. Let's just say here, sometimes in a more practical setting, it's we're use S. Okay. So, but these two letters are reserved for the universal set. Call it whatever you will, the set of everything. On the other hand, we have the concept of the empty set. Anything like this is sort of an extension of the number concept. Number concept is a single thing that represents a quantity. Here we have uh, things that are actually collections of other smaller things. You still need the concept of everything and nothing. This is simply the set, let's say you're containing, set containing no elements. It's empty. So it doesn't really matter what our example is. It's irrelevant because it won't contain anything. Now we can write, or let's write, may want to write curly brackets with nothing in it. It looks a little weird to have nothing in it, especially if I'm now combining these sets and listing them in sort of combination with each other and make more complicated things. Just two curly brackets with nothing in it seems a little out of place and can be misread easily. So this is a little sloppy, though technically I suppose correct. We'll give it a name. Special symbol to always refer to the set that contains nothing. And we'll use the Greek letter phi. So it's just a little bit easier to read if it has its own symbol instead of brackets with nothing in it. That's weird. It can easily. So we give it its own name. That is the letter, Greek letter phi. We'll refer to the set that has nothing. Okay. So we have a whole bunch of little things, focusing on our example, little combinations of collections of little letters. Could be everything, and could be nothing. And of course, many things in between. Okay. So we're just getting the language that we'll use, the words that we'll use when we talk about these collections of things called sets. And it'll be a little bit slow in the beginning, but we'll build up to eventually solving problems using these and so on and see how they are used and why they're necessary and so on. Right. The next is the concept of a subset. Now, many of these words are sort of chosen to have a connection to what you would think they mean, but let's clarify it anyway. So I want to make a general statement here of what we mean by subset. So I don't want to refer to these specific sets. I'll refer to just sets in some set in general. So I'll say set E. Could be anything. could be in the context of this, but I don't specify it because I want to make a general statement of what the subset word means. So set E is called a subset of some other set F, let's call it, if each element in E is also in F. Now let's go back to our example, these four examples and the context of lowercase letters, and let's see which one's a subset of which one. Well, I'm looking for a set so that each element is contained in some other set. If I look at A and B, every element that B, big B, set B has, little a and little b, they are also contained in set A. Set A may have other things as well. That's okay. There's no requirement for it to have or not have. Might be much bigger. But everything in set B is already in set A. And I can therefore say that set B is a subset of set A because everything it has is also in set A. You can think of it as set B is contained inside set A. Set A is bigger in this case, but B is a part of it. B doesn't have anything outside of that. Now, these words are perfectly fine, but often in math, people want to use symbols and make things as compact as possible. Sometimes they go too far, but in this case, it's okay. We have a symbol to capture and represent these words is a subset of, and the symbol is called the subset symbol. So when you see this, it is just a mathematical word or a symbol or word for the phrase is a subset of. Okay? So these are interchangeable. English language, sort of. Mathematical language, more pure. I can also say something's not a subset of something else. If I look at A and C, set C, has a little c that does appear in A, but it also has a little d and a little e that does not. So set C is not a subset of set A. Set C isn't completely contained in set A. So we could say that as another example. Set C is not a subset of set A. Now, of course, I want to symbolize this as well. We're going to use the subset symbol, which is sort of like a flattish, longish little C with a line under it. But now it's a not, so I'm going to put a line through it. Not a subset. So I can recycle the symbol for is a subset of, and when it's the negative, the negation, it's a not. Line through it. Okay. So some sets are contained in other sets. Some sets are not contained in other sets. Some sets are subsets of other sets. Some sets are not subsets of other sets. All right. Okay. So let's say here a special case that you might think of as special. Special cases, rather. If I still look at my example, and now think about the universal set, which remember contains everything. I claim that every set, this example, and any other combination you could make, is a subset of the universal set. Because by definition, the universal set necessarily contains absolutely everything. lowercase letters of the alphabet in our case. So any combination of lowercase letters, any collection that you want, that you could possibly have, will necessarily be contained in the universal set because the universal set contains everything. So I could say here any set, let's call it E, is a subset of its universal set. Of course, they have to be sort of related to each other. If I talk about letters of the alphabet, any collection of letters of the alphabet will be a subset of its universal set. It has to be in context. So we could make this a little bit more formal as a more mathematical statement. We could say for any set E, E is a subset of the universal set. Or let's actually not make a comma there. Let's make a any set E, it's true that E is a subset of the universal set. E specifically, but for any other set of lowercase letters you could possibly want to make. Make that special case 1. Special case 2, I'm going to say the following. Any set called E is a subset of itself. I'll make the statement a little bit more proper. For any set E, E is a subset of E. Well, I'm really just testing if I understand the subset concept by taking my time and looking at some special cases, looking at some examples, and so on. What do I need for the subset concept? I can say it in two ways. If I make a claim like this, or I could go up to the top. I make a claim like this. Everything that B has to be in set A as well. I could say it another way. B doesn't have any elements that do not feature in A. Either way, I get this containing effect. So if I look at the set itself, everything that E has. Or, put another way, there's nothing that how should I say it? Yeah, there's nothing that E has that's not in E as well, because it's the same set. So the set is contained in itself. This right-hand set doesn't have to have more elements or be different. We could have the special case that it's contained in itself because it has its own elements. There's nothing it doesn't have. I just want to be careful with my words here. There's nothing it has that the right set does not have. There we go. Really just letting the subset concept sink in, taking my time. Now we have the other special case. At the other extreme, I used the universal set. So I want to say something about the empty set as well. Say it like this. In words first, the empty set. This one's going to feel a little strange, perhaps. The empty set is a subset of any set. Formally, for any set E, the empty set is the subset of it. Now here it's a little tricky because my original explanation of subsets requires that any element in the left one should also be in the right one. But this left one doesn't have any elements. So I'd rather think of it in the other way. There's nothing that the left one has that's not in the right one because it has nothing. It's like comparing the number 0 to a positive number. Initially, for little Timmy, it might seem strange because he has nothing to compare. 0 means you have nothing, but nothing is less than something. Even though you can't see the nothing, it's still there. So think about this one. Let me know if you sure. But we have these special cases as well. Just giving us some time to let the subset concept sink in. Now, I don't really care which version of a statement you are comfortable with. It could be completely in words. It could be a little bit more formal with the subset symbol. I don't really care, right? It's just a translation issue at this stage. The meaning is the same. Subsets. So now let's just make a new page here. We have an not example, exercise in our book to give us. There's a lot of little things that the discussion on sets, even though it starts slowly, that it can, that it teaches us. A lot of little things. Of course, I have most of it. Subset concept, universal set, empty set, blah, blah, blah. 5.1. I have a set, little letters A, B, C, D. Question is, how many subsets can I make? Okay. So at this stage, there aren't many exercises, but this is a question we can do. So this is now, let's say, the original set, A, B, C, and D. Okay, so now we've had this idea before when we looked long ago at general problem solving in 142, and uh, we had to just arrange all the letters. One of the very first questions. If I assume little Timmy understands the subset concept, whether I call it a subset or not, I want to make selections of these letters, right? It's a subset concept pretty much. How many different selections can I make of this? What is he most likely going to do? He's just going to, assuming he understands the question, now he knows what to do, what he's looking for. The question is, how is he going to go about finding all the possible subsets? Most likely, he's just going to start, well, you might want to make a table, but the question is, what is little Timmy most likely going to do? He's not going to make a table. I'll put money on the fact that he will not make a table. That is not the first thing that comes to mind without some experience. He's just going to randomly start making subsets. Oh, maybe there's one. I can choose those two letters. I can choose maybe those two. I can choose a C and a D. Oh, I can just choose a B. Oops, no comma, just a B. First of all, these are all subsets. So he is correct that these are subsets. The question is, how is he going to go about it? And if he does just randomly go about making subsets, you ever going to be 100% confident that his list is complete? Probably not. He's just going to hope for the best. And if it's all shuffled around like this, I'm not going to be confident when I'm done. Do I have them all? I don't know. Random strategy is not going to work. Well, it might work. I'm just not going to be confident to know when I'm done. So all the way back. Perfect. So we want to do the same thing, but we want to do it in a structured way so that by the end, we know for a fact we have them all. That's the difference. So I'm going to start by looking at the size of my subsets. First one is the empty set is a subset of anything. That's one I can easily forget. Essentially, it has nothing in it. Let's say here size 0. It has nothing. Then I can go to size 1. All the single element subsets. Please ignore the sloppiness of my curly brackets. They're curly brackets, even if they don't look like it. I can choose a subset. I can have a subset that is choosing just one letter every time. So now I'm systematically working through my possible subsets by size, for example, and by the end, I'll be much more confident that I have them all. Just randomly picking them, I could easily miss one, especially if I have more letters to start with. Okay, now size 2. Well, I could have an A and a B, and even within this size 2 group, I want to have some structure. I want to stick to the first letter and then say, okay, A with B, A with C, A with D. Now, the ordering within a set doesn't matter, right? So I couldn't have anything else paired with A. I only have 3 other letters. But I could have B. Now, I'm not going to write A again, right? Because that's the same as this one. There is no ordering. So I only need to look forward. B with C. B with, look at that curly bracket. Wow. B with D. And then I'm done. B has been paired with each of the other 3 letters. Then I can look at C. C has been paired with A and B, but not D yet. And then D. D has been paired with all 3 other letters. Now, because yes, I'm structuring my list by way of size, and when the size gets a little bit more interesting, I want to have some structure in that little list as well. So that by the end, when I write the CD set, I know there are no more of size 2. I am 100% confident because I can explain how I made them, how I listed them, and I can convey that confidence to someone else. Well, then I'll go up to size 3, where I have to be a little more careful. I'll fix the first 2, A and B, just as they appear. And then it could be paired, so to speak, with C or with D. Now, I can't keep a hold of A and B anymore. I'll keep A, but maybe focus on A and C. Now, A, C can be paired with B, but that's been done. So it still has to be paired with D. Then I can try and hold on to A as much as I can and focus on the pair AD being paired with something else. Well, AD has already been paired with B here and with C there. So I'm kind of stuck. I only look forward based on my systematic way of listing them. I'm only going to look forward, and there is nothing else to attach to the AD pair. Looking back would just double up on what I already have. So that's as far as I can go with my A. I've paired it with everything I possibly could while still having the option of looking forward. So I could also then look at a pair BC would be next, and that still has something forward to be grouped with a D curly bracket there. Then I don't have anything else to do without doubling back and finding something I already have. So of course, the more things I have to look at, the more little letters, the bigger the size, the more difficult this arranging list is going to get. So for my systematic way of getting through this, I sort of have to look at an arrangement just to keep track of everything. But the set ultimately does not have any arranging, which is why I'm only looking forward. And then, of course, there is a size 4 subset because every set is a subset of itself. The set itself is also a subset of the set. And then I count them all. How many do I get? Well, here I have 1, here I have 4, here I have 6, here I have 4 again, and here I have 1. So 5, 11, 15, 16. So total number of subsets is 16. All right. Now, yes, you could see perhaps already that if I made my original set bigger, making this list is going to be very much impossible after a while. But that's not our goal really here. Right now our goal is to understand the subset concept and as a bonus, uh, be aware of this sort of systematically and logically making a list and working my way through it so that at the end I'm confident in my answer. Randomly making entries in this list will not give me that confidence. I'm even lucky enough to get to 16, I could easily miss one of these, right? Or I could double them up very easily. I think that's more likely. If you randomly let little Timmy randomly make his list, he's gonna probably double up one that he had early because it's hard to search through the list to see what you already have. That's more likely, I suppose. So there's a lot of little things I could learn here and add to my experience within this set topic, of course. All right. So I think we've gotten a lot out of our subset concept here. Now we do have tomorrow as well, but I'm just gonna keep going. Time runs out, and if we end early, that's great. More time for questions. And if I just want to make sure that we get through everything we need to get. Eventually, eventually. So if you look at the book here, there's more things you could read if you want to, but covers pretty well. Now, if we look at our original example, we now have a good number of words here, right? We have universal set, we have empty set, we have subset, and we got time to learn and just emphasize what they mean. If I look at these examples, there are ways to take these sets, combine them to make new sets, new collections built on these. Let's look at two ways to do that. The first way is the union. Now I'm going to say it in general without specifying any sets, but then we'll come back to the specific examples. So just bear with me while we write out this sentence. The union of a set, let's call it E, could be anything, with another set, call it F, is a potentially new set. And we're going to call it E with a little cup symbol. That's my union symbol, F. It's potentially a new set. Usually, it needs a new name. But because it's going to come from combining E with F in some specific way, I want to have the new name refer to those original sets. The new set is going to be named. I emphasize that. This is just a name, named E cup F. We'll read it as E union F. And this new set that contains each element in E or in F or in both. It's not a U. It doesn't have a little line there. Not a letter, it's a symbol. It's the cup symbol. But you can think of it as a little U for union. And if you write a U there, it can't be a big U, right? Because big U is universal set. So this the closest it is to a letter is a little U, but it's not a little U. It's a symbol. It's the cup symbol. It's the union symbol. See, look at this. Cup symbol, letter U. It's like night and day. See, it's not the same thing at all. However, since it's so convenient to think of U for union, if you want to write a little U there, I'll look the other way. So I'm making a new set. I know it's night and day. They don't look the same at all. I totally agree. New set contains everything that E contains, or it could uh, come from F as well, or it could be elements that happen to be in both. Let's have a look at our examples. Jump back and forth here. Here are our example sets. Let's take A with C. A union C. So even though it might not make sense to you right now, please take note that I am never using the word and when I talk about union. I'm never saying A and C for reasons that'll come up soon. I'll say the union of A with C. I'll say A union C. Don't ever use the word and here. So I'm making a new set. Whew. Let's assume that's a curly bracket and move on. So this new set is going to contain everything that A contains. So little a, little b, little c, that's what A contributes. Or the elements in my new set could also come from the second one, C. C or big C, set C, has little c, little d, little e. I already have little c in my list. So there's only one letter C. It happens to be in both. So I'm not doubling it up. But C does contribute some new letters, little d, little e. So don't write two C's. That's never going to happen. There is only one letter C. It just happens to be in both. So when I look from left to right at the contributions that these individual sets make, I already have it by the time I look at the second one. So really, this is a merging of the two sets, so to speak. Everything that any of these sets have, I pool it all and make a bigger set. Throw them all together. No discrimination. Just everything comes along. Just don't double up anything. Sometimes there might be no overlap. A with D, A union D. Well, set A contributes some letters. Set D contributes some letters. No overlap at all. So even though the originals contain 3 letters each, you see the union might contain 6 or might contain 5. It really depends on what they are. What about A union B? I have to look at them to remember. I just go left to right, whatever. A contributes little a, little b, little c. Set B contributes little a, little b, but it's already in there. I already have them. So B doesn't contribute anything, really. Which leads me to an observation. And I want to make these observations slowly so that I can get used to this union that I just defined a minute ago. Very important. So let's note this last one. What does this tell me? Set B doesn't contribute anything new because set B is a subset of A. So when I then look at the union, set B is kind of useless because set A already contains it. It's not going to contribute anything new. So remember here that set B is a subset of set A. And when I do the union, which is throwing everything together, whatever A contains, those are the elements. B doesn't have anything new. So if I have two sets and one set is a subset of another, then their union will be the bigger one because being a subset means being contained in this quote unquote bigger one. I know there's a special case it might be the same. I try and think of it as a bigger one, just intuitively. Because the left one's already contained in the right one, when I throw them together, I only have elements from the right one. The small one does not give me anything new. That's one. Next, if I take any set and I take the union with the universal set now, see cup symbol, big U, get a little line extra. What do I get? Well, the universal set already contains everything. If I combine that with any other set, that set is necessarily a subset of the universal set. So when I throw everything together, I'm getting the universal set. So it's very important that we understand these little notes and examples, but the notes more than anything else, because it's sort of a little test. Do I understand the instructions that the union gives me? If I take the union of two sets, it comes with instructions for how to combine the elements to make my new set. Last one. For any set E, I want to look at E union empty set. Now I know it's a lot. If you've never seen these things before, it's a lot for day one. So we'll just stop here. One more. Actually, no, I'll do a little more, which will help me for the union. Well, any set E thrown together with nothing, just be E. There's nothing to merge with. Tough to think about, but you are not wasting your time if you think about these things and let them be nice and solid in your understanding. Just to visualize these things. We have 4 minutes, we can do it. Now, there is another way to combine after union, but I'll do that tomorrow. By way of a Venn diagram, we can visualize sets very nicely. I'm going to have a rectangle. That rectangle represents everything universal. There is nothing outside the rectangle. Every possible element you can make in the context of whatever you're looking at is in here. Then we'll have some circular shapes to indicate specific sets. If we refer to our example, set A will be maybe something like this. That'll be A, and it'll contain little a, little b, and little c, and all the other letters will be outside. If I look at set C, it has little set C, D, and E. Well, that has an overlap, right? It overlaps in, let's see, little letter C. So set C has an overlap with A, and then it has its own things. Over here could be set D, which doesn't have any overlap with any of the examples. And if we look at set B, well, that contains little a, little b, so that'll be over here. So you see now the subset concept is literally, in terms of the Venn diagram, B is contained inside A. B is inside A because everything it has is already in the A circle. I'll call these circles even though they're circular. All right. So now when we look at our union, it'll concern two sets. Now I don't know always what those sets contain. I want to have a general layout to cover every possible overlap that could happen. Let's call this first set E. The other set, that's called F, has to be positioned like this. Cover everything that's possible. There's stuff outside that none of these sets have, possibly. There is something over here that set E has that F does not have. There's potentially stuff here that F has that E does not have. And there's potentially an overlap as well. Covers all the possible places elements could occur relative to the sets E and F. So this is the general position for two sets in my Venn diagram. The union, E union F, let's color. E union F. Remember, we're merging, we're throwing together E with F. So anything that's in E needs to come. And maybe F has some new things to contribute as well. So I could visualize where the new set E union F is located. Every element that is in this in these blue regions that makes up the union. Now, in some cases, one could be a subset of another, and then one of these regions, maybe this one, is just empty. I can always start with the general layout, and then if I have more information, I will just realize that one of them is actually empty. But there's no harm in starting with this one. I don't want to specialize and miss out on a region when I don't know for a fact it's gone, actually. In our example here, we knew exactly what set B and set A contained, so I could put it inside. But very often, we won't know exactly what the elements are from the beginning, so we want to make sure and cover all the possibilities. We'll pause here and look at the other ways to combine sets next time, but there's already a lot to think about that will help you forward with this topic. So take the time and make sure it's nice and solid if you can. Are there any questions at this stage? We need to have some time here first before we're able to do any problems. So don't look at any problems yet. We need tomorrow before we can start looking at more practice problems. Right now, just think about what subset means, think about what union means, and all these little key words, and we'll be okay. Any last words? All right. Just typing. Let me just check. All good. Thank you. Thank you. So we'll continue this then tomorrow. Until then.